Math 2414, series, video 3, geometric series. Full disclosure, I am going to approach this topic a little more generally than the author of the textbook that I'm referring to. For those in my class, of course, that's Stewart's Essential Calculus, Early Transcendentals, second edition. But I'm going to treat geometric series a little bit more generic because the formula given in our book is really specific. And I'll show you what that is here in just a second and why I think my version's a little bit better. But anyway, let's take a look at a geometric series. Now, we've seen the word geometric already in terms of a sequence where the way that you move from one term to the next was by multiplying by a common ratio. For example, if we had a sequence 5, 15, 45, 135, etc., then you could deduce that this is a geometric sequence because the common ratio to multiply from one term to the next is 3. It's called a ratio because if you take the ratio of consecutive terms, for example, 15 over 5, or 45 over 15, or 135 over 45, those all have the same common ratio of 3. Let me do one more thing before we go any further. I've been trying to use a thinner line width, and some of the things I'm drawing just aren't coming up good, so now the line width's going to be all right. So anyway, so a geometric sequence was a sequence where to get from one term to the next, you multiply by a common ratio. The geometric series is just the sum of a geometric sequence. In this case, the geometric series is a series of the form, the sum from k equals 0 to infinity of a times r to the k. Because if you were to start with the lower limit of 0 and putting it in for the k, for the index, you get a times r to the 0, but r to the 0 is 1, so a times 1 is a. If you put in k equals 1, you would get a times r to the first, so a times r. If you put in k equals 2, you would get a times r to the second, and a times r to the third, and so on. So you can see that the common ratio that you're multiplying is times r, because each term is picking up an extra factor of r. So as a sequence without the pluses, it is geometric. So as a series, it's called a geometric series. Now, what's different between the way I do it and the way the book does it? The way the book shows the definition is they say the sum from k equals 1 to infinity of a times r to the k minus 1 in the exponent. So that the lower limit starts at 1, but when you put the 1 in, it gets 1 subtracted from it, so you get a times r to the 0, so it actually plays out exactly the same. I personally don't feel like forcing the minus 1 in the exponent is necessary, because if you did have a minus 1 in the exponent, you could always split r to the k minus 1 as r to the k times r to the negative 1. And if you have an a in front of all of it, then you can just write it as a over r times r to the k. So you can write it as a k power instead of k minus first power. And actually prefer for the exponent to be just the index, not the index plus or minus something. So it's not necessarily wrong or better. Well, personally, I think my definition is a little better because the exponent doesn't have a minus 1. It is equivalent to the author's definition. But I have an even more generic approach to describing a geometric series, and more importantly, what it converges to and when it converges. And when we get to the end, I'll show you what. All right, so if we're going to address the situation about whether or not this converges, then we need to look at its sequence of partial sums. And more particularly, if we can find an expression for the nth partial sum, then we can just take the limit as n goes to infinity. So let's look at the nth partial sum of the expression that I'm using to define a geometric series. The nth partial sum, by definition, is the sum you get when you stop the sum at n, a times r to the k. So we would start out with an exponent of 0, giving us just a, and we would progressively raise the exponent on the r until we got to an exponent of n. And as a finite sum, as a partial partial sum, it would stop there. So that's what our nth partial sum would look like. So can we come with a closed form expression for this? Because remember, what we're trying to do is take the limit of it, of the nth partial sum, and as long as it's not a closed expression, meaning it doesn't have these three dots in the middle, then we can't really take the limit. So we're going to do a little bit of trickery here. This is the standard proof for calculating a partial sum for a finite geometric series. The trick is to massage the right side of the equation until you can get the sum to show up again. And the way we're going to do that is we're going to move some things around. The first thing I'm going to do is I'm going to move this a to the left side. So we have partial sum minus a. Now I'm going to leave a blank space there because I'm going to put something there in a moment. And we'll leave the rest of this. And notice that I just lowered the number of terms on the right side by 1. So it has 1 fewer terms than it originally did. Now, I'm going to add something to both sides. I'm going to add what would be the next term. Next term we would get by simply raising the power by 1. We're going to add a times r to the n plus 1 on both sides. Not sure if I left enough room there. I'll make it work. All right, now why would I want to do that? Well, number one, it restores the right side to the correct number of terms from the partial sum. The right side still has n terms. I just moved the original first and added on the next one to balance out the number of terms. Now, if you look at the right side, you'll notice that there's a common factor that we can factor out. All of these terms on the right side have an a and an r. Some of them have more than one r, but not all of them because of this. So I can factor out both an a and an r from the right side, but I'm not going to quite factor out all of that. I'm only going to factor out an r. Here's the left side. If I factor an r out of the right side, I'll get a plus ar plus, we get to the n, a times r to the n minus 1 plus a times r to the n. Everybody just gave up one of their r's. Now, why is that useful? You recognize what's inside the parentheses. Expression inside the parentheses is precisely this. Granted, I didn't show the same terms. I didn't show the AR squared on the bottom, and I didn't show the AR to the n minus 1 on the top, but those are the same sums. And because of the same sums, that means that I can replace what's inside the parentheses with this. So let's replace what's inside the parentheses with that. In fact, I'm going to pause the video and make myself a little bit of room. Got to remember that I can pause and make things happen without wasting your time. All right, so as I was saying, the expression inside the parentheses is equal to the nth partial sum. So let's rewrite this equation with the nth partial sum replacing the parentheses. And now that I've got Sn embedded in this equation, I can just solve for it. To solve for this, we're going to move some things around. I don't know if there's a best order in which to do this, but I know what my end goal is looking like, so I know what I want to move. I'm gonna solve for Sn by moving this guy over to the right, to the left side, so that all the Sn terms are on the same side. But at the same time, I need to move the terms that aren't Sn away from the Sns. So if we grab these guys and move them to this side, we'll have all the Sns on one side and we'll be able to factor out and solve. So let's do that. This first Sn alone, because it isn't moving, the r times Sn is getting moved from the right to the left, so it changes signs. The minus a is being moved from the left to the right, so it changes signs. And the plus a to the n plus 1 is being moved from the left to the right, so it changes signs. And now all I have to do to solve for Sn is to factor it out, leaving 1 minus r. And then if I divide both sides by 1 minus r, I get that the nth partial sum is equal to a minus a to the n plus 1, 1 minus r. Something is amiss here. That's not what I was supposed to get. Oh, I know what some of you were thinking. You lost something. 1 second, folks. Let's pause this video. Damage control. Sorry, folks. Had the home phone ringing, and it was a spam call, and I should just let it go. And we were in the midst of doing some damage control. And I don't mind making mistakes on these videos. I know it takes more time, but it also points out that it does not matter how good you think you are, we'll make mistakes. And compared to you, I'm the expert. If not compared to you, I'm the expert. So if I'm prone to make mistakes, then you know you can't do it. The mistake I made is when I went from here to here, I lost the R. And so what problems did that cause? Well, let's undo it. Sorry if you were writing everything, but it's going to happen. So let's fix this. All right. So this is supposed to be r to the n plus 1. That back highlighted in orange because I kind of liked it that way. And now let's play this out again, but I'll play it out a little bit quicker because now we're doing it the same. All right, so we have all the s's on one side. On the other side, we have a minus a times r to the n plus 1. And then if we factor out the Sn on the left, we get 1 minus r. And we divide both sides by that. And we get that the nth partial sum is a, which I'm going to factor out, times 1 minus r to the n plus 1 over 1 minus r. All right, so since that's the nth partial sum, we can determine whether or not the series converges by taking the limit of that as n approaches infinity. Notice in the nth partial sum that the limit, the n is only in one place, right here, and more specifically, it's an exponent on this r. So whether or not the series will converge is 100% dependent on what that r to the n plus 1 will do as n goes to infinity. Let's take a look at it. The nth partial sum was a times 1 minus r to the n plus 1 over 1 minus r. And the question we need to answer is, what is the limit as n approaches infinity of Sn? But again, because the n is only the exponent on the r, this really boils down to what is the limit as n approaches infinity of r to the n. Because once we know what that does, or rather I should say n plus 1, once we know what that does, then we can import the results in over here and figure out whether or not this limit of the partial sums converges. Wait a second. We've played this game before, back in the previous series of videos. That is just a power series, a power sequence, and we know exactly what happens to a power sequence in terms of convergence and divergence. So here's what we know. We know that this will converge to 1 precisely when r is equal to 1. We know it converges to 0 if r was between -1 and 1. Again, this is from the previous series of videos, so I'm not going to reteach it now. But we also know that it diverges otherwise. So we've got some conditions on the r that will make this limit exist. So let's take them one at a time. Let's start with the case when r is equal to 1. When r is equal to 1, that means that this will converge to 1, and we'll get 1 minus 1, which is 0. But if we put r equals 1 there, we'll get 0 in the denominator, and we'll get technically an indeterminate form, but for now we'll just say that that does not give us convergence. So under this condition, that's bad. Do it twice. That's bad because it gives us 0 in the denominator for the formula for the nth partial sum. Clearly, if the r to the n plus 1 diverges, then that's going to blow up, so that's not good. So we don't get divergence there. But look in the middle. What happens when that limit is 0? In other words, what happens when the r is between -1 and 1? then that means that this thing will go to 0, which means everything else collapse. Everything else will clean up real nice. So if -1 is less than r is less than 1, and you know what, there's a more compact way to write that. The absolute value of r is less than 1, puts it between 1 and -1. Then the limit as n approaches infinity of the nth partial sum is going to be a times 1 minus 0 over 1 minus r. That's just a times 1 on the top. So it's a over 1 minus r. And we have now two things. We know when a geometric series will converge. That is when the ratio has an absolute value that's less than 1. And when that happens, we know what the series will converge to. I think we need to summarize this. Sum of a geometric series. And remember, a geometric series, the way I'm writing it, is the sum from k equals 0 to infinity of a times r to the k power. So it's a plus ar plus ar squared plus dot, dot, dot. If a geometric series has a first term of a, and a ratio of r, so r is what's getting multiplied to go from term to term, and that ratio's absolute value is less than 1, then here's what we know. Sum k equals 0 to infinity, a times r to the k is equal to a over 1 minus r. That's cool. Now, before we go any further, I want to write this formula a little bit more descriptively, because you will run across geometric series that don't start at 0, that are all jacked up in here. But if you can identify it as a geometric series, meaning you are multiplying by the same number to get from one term to the next, and that number's absolute value is less than 1, then the sum of that series will always be first term over 1 minus the ratio. To me, this is a lot better than a over 1 minus r. Because saying the sum is a over 1 minus r means that your series needs to look just right so they can go, there's the a, there's the r. But if you know it's a geometric series, then you really don't have to worry about what you call a and what you call r. You only have to know what's the first term, what am I multiplying by, and is that thing's absolute value less than 1? If it is, then the thing in the cloud is my sum. To show you that this does work with something that we saw before, and then we'll wrap up this video that's going longer than I expected. This is something we saw in the previous video. The sum of 1/2 to the I power as I goes from 1 to infinity. If we wrote it out, we would get 1/2 plus 1/4 plus 1/8, etc. But this is a geometric series because the ratio of consecutive terms is constant. Or equivalently, we're multiplying times 1/2 every time we go from one term to the next. So that means that our ratio is 1/2. Well, it's pretty clear that the first term is 1/2 also. Now notice I didn't have a 1/2 part in front of here, like there's an a part in front of there. I'm not worried about it looking a certain way. I'm worried about it behaving a certain way. If my series is geometric, meaning I multiply by a constant to get from one term to the next, then, and if the absolute value of the ratio is less than 1, which it is here, then the sum will always be first term, which is 1/2, 1 minus the ratio, that's 1/2 over 1/2, which is 1. We'll take a look at another example of a geometric series in the next video because this one's gone a little bit longer than I wanted.